So this exercise in here is a reminder, I guess, on how to solve second order differential equations. Because this is kind of the bread and butter of vibration, you know? Everything will become a second order or first order, in most cases, second order differential equation. Why? Because the key equation that you will see over and over again is in this form. Mx dot dot plus Cx dot plus Kx is equal to some function of time, right? And the goal behind solving this is to find really what is x of t, right? After you find x of t, then you can find what is x dot of t, and you find what is x dot of t, meaning that any time you can tell where the position of the mass is, what its velocity, what is its acceleration. I mean, that's really what the goal of vibration is. You have something that vibrates, and you are trying to say, okay, how am I describing that vibration? Well, it's a dynamic event, and dynamics, we say that it's position with respect to time, velocity with respect to time, and acceleration with respect to time. So most of our equations will be in this form. Like for example, in here, I'm gonna try to follow here on this slide. On the lab. It says the objective of this lab exercise is to review how to solve differential equations using the traditional methods, Laplace transforms, and MATLAB, 3 different methods. Okay? Let's start with the first one, which is the traditional method. And in general, when you have a differential equation in the form of y prime prime plus k1 y prime plus k2 y is equal to 0. Now you may ask, why am I using prime prime and why am I using dot dot? Do you know why?
Not a clue.
What's that?
Because you told us to.
This still means the second derivative, right? So it kind of means the same thing. This is kind of, the dot dot is specifically used when the variable that you are differentiating with is time, right? But this one, for example, could be d squared y over dx squared, for example.
Okay.
We can call this y prime prime, dy over dx could be y prime, etc. But again, in terms of handling the math, it's still the same thing. So, what is this? Second order differential equation with constant coefficients, right? And the way you approach this in the traditional methods, the first thing you need to do is to write the characteristic equation. The second derivative becomes r squared. Why are we using r? Because we need to find roots. Some other textbooks use the letter m, but it's really the same thing. So r squared plus k1, first derivative, that means r to the power of 1, or kr, plus k2, here there is
R to the power of 0.
r to the power of 0, or just k2, right, is equal to
0.
0. Okay? So this, what is this now? This is
Simple
a quadratic equation, and we all know how to solve quadratic equations. Remember,
Minus b.
r is equal to plus or minus
Derivative is minus b plus
minus k1, right?
No, never mind.
Plus, sorry.
Negative b
Minus b
so
plus or
Minus
minus
k1
plus or minus
square
root
b
root of k1 squared minus 4
times
k2,
1.
a c.
right? Divided by 2, something like this, right?
Or use your calculator.
Or you do.
That's true.
I've been practicing.
In other words, you're gonna have 2 roots, right? So how are the 2 roots gonna look like, right? If, we call this the auxiliary equation or the characteristic equation, if the 2 roots are real, okay? I'm not gonna write what's written in here, just to make it fast. The 2 roots could be real. If they are real, let's say, for example, you get a value of 2 and a value of 3, then the solution becomes simply y is equal to some constant a1 er1t plus a2 er2t. Done. Because you will have calculated r1 and r2. Now the only thing you will have to do is a1 and a2. How are you going to get those? Initial conditions again. Okay. So those are if the roots are equal, are real. Now, but real and different. Sometimes you will have one root which is a double root. In other words, the roots are the same. It's like maybe the characteristic equation can be written as r minus 2 squared equal to 0. What does this tell you? That r is equal to 2. Make sense? Right? So if the two roots are equal and the same, then the equation can be written as a1 art, right? So you can either have y is equal to a1 er1t plus a2 er2t, and this is two roots are real, right? Or you can have y is equal to a1 ert plus a2r, sorry, a2 t ert. Okay, this is if you have one root, two roots which are the same.
The next page where you have it in gray, where you're giving an example.
Mm-hmm.
Now I'll let you take us through it. I have a question when you get to it.
Okay, so if the two roots are imaginary on the other hand, and that's really what you get the sinusoidal stuff, when the roots are imaginary, right? Then you get y is equal to a1 e alpha t cosine omega t plus a2 e alpha t times the sine of omega t. Where the constants a1, a2 must be defined from the two initial conditions. So in the first part of this, it just gives you all the three possibilities. Two real, one real which is kind of the same, or two reals which are the same, or you have imaginary solutions. By the way, when you say imaginary, that means it's either alpha plus I omega and alpha minus I omega. Remember how these two complex numbers are called? Said it earlier. When you have a plus ib and then a minus ib. Complex conjugates, okay? Conjugates. Okay, example. And this is what I want you to kind of go through. What if we have y prime prime plus 6y prime plus 9y equal to 0? Okay, with initial conditions, y of 0 equal to 0, y prime of 0 is equal to 1. Initial position is 0, initial velocity is equal to 1. How would you solve this one by hand? Remember what's the first thing you need to do? Write the characteristic equation, which is what? R2 plus 6R plus 9 is equal to 0. Right? And what are the roots of those?
-3, so the same in equal.
Well, R2 minus or plus 6R plus 9 is equal to 0. If I didn't have a calculator, I wanted to use just this one. What is R12 equal to? Well, minus B, which is minus 6, plus or minus square root of delta, which is B squared, which is 36, minus 4 times 9, which is 36, divided by 2, right? So this one is obviously 0, so you're going to get minus 3. So both of those roots are minus 3. Under which category that falls? Both of those are real and they are the same. That means your solution has to take up this form. In other words, yt is equal to a1 e minus 3t, because the roots is minus 3, plus a2t e minus 3t. Now, the only thing you have to do is find out what the solution is,
And
right?
that's my question, because if A1 equals 0, is it just because you're using?
Now, darn it, applying the initial conditions. Okay, so let's look at that. Yt is equal to A1 e minus 3t, right? Plus A2 t e minus 3t. What are the initial conditions? Y of 0 is equal to 0, right?
Right.
But if I replace t by 0 here, what do I get? Help me out.
You get A to the E, right? No, I mean, actually,
What's e of 0?
Is it one?
One.
It's just 1. So I get A1 times 1. How about this one?
Zero.
That's 0. So that means that A1 is equal to
Zero.
0. Because that's what I'm told. I'm told that y of 0 is equal to 0. But y of 0 is also equal to A1, right? That means that A1 is equal to 0. Now, another exercise here. What is y prime of t? Based on this equation. Forget about this. Based on this.
Minus 3 A1 e to the negative 3t.
Huh?
Minus minus 3
Minus three.
A2 t squared e to the negative.
Okay, slowly. Minus 3t, you see?
Minus A2.
3, A2, so minus 3, okay.
Whatever, yeah.
Minus 3,
Minus 3,
A2,
A2,
T
t
squared.
squared
t squared
e to the negative 3t.
in negative 3t. That's it?
Oh, shoot.
That's totally
Chain
wrong.
roll. There's a t in there.
This is a t. This is not correct.
Oh, so it's gonna be.
Remember when you have
Two.
uv
Dang
and
it.
you take the derivative, what is that?
It's u prime v
U-
plus v
U prime v plus
V
u
prime.
V prime.
v prime. Okay? Let's say here plus, let's forget about a2 for now, right? So think of this as u, think of this as v, right? So what's u prime?
e2.
Well,
Oh,
if
sorry,
it's
sorry.
just-
If it's t, it's just one.
One.
It's just one,
Sorry.
right? Okay, so it's gonna be 1 times
E to the
e
negative
minus
3t.
3t. Now plus
Plus
u, which is
T.
t times, what is v prime?
minus 3
Minus
minus 3 e to the negative 3t.
Minus 3 negative e to negative
3t.
3t.
Oof.
Product rule.
yeah.
Okay? So, we already said that a1 is 0, so we don't worry about this guy, right? But we said that y prime of 0 is equal to, what did I say? It's 1, right? So, using this equation now, help me. When t is equal to 0, this is equal to, well, a2, right?
zero.
a2.
It's just A.
What is this one?
That's 1.
That's 1. What is this guy?
0.
0. So that means that A2 is equal to 1. See, that kind of corresponds to what I have there. I didn't go through the details of it.
But, no, but,
Hold on.
But
when you get to the solution, it's y of t equals a1 e to minus 3t plus te to minus 3.
oh, I should have said, oh, sorry. So it should be just T, yeah.
That's
I have
why
to
I'm
take,
confused.
yeah. We have to remove that A1 e minus 3t because A1 is 0.
Yeah.
Yeah, thank you.
So,
I'm gonna correct mine.
okay.
It's
so-
not wrong, it's just confusing.
Yes,
Yeah.
because it's bad enough without my understanding, so so it's just plus 3t.
So it should be just, the solution will be simply y of t equal t e negative 3t. Does that make sense?
Yeah,
Because A1 is 0 and I forgot to replace A1 by 0.
yeah, gotcha.
Is this in this book? This,
No.
Is it in the book? No. No, this is just some
So
imaginary things, yeah.
y is, so in this, and y prime of 0, minus
Yes.
3 ae to the negative 3t,
Uh-huh,
why is that not 3, or negative 3? Did it go
because
cancel?
t is equal to
Because
zero.
T zero.
I mean in the first part, when you have minus 3 ae to the negative 3t.
Y prime,
A1 is equal.
because A1 is equal
Oh,
to
that's right.
zero. All right, are we good then, up to now?
Yeah.
Okay, so by hand, that's how you do it. If we got solutions that were too real, right, then we would have used this. If they were imaginary, we would have used this. But applying the initial conditions will be exactly the same way. Now, using Laplace transforms,
By hand, oh my god.
right? Laplace transforms, by definition, Laplace transform always transforms a time domain into a complex domain, S, okay?
So, sorry, is this, I don't know, I don't remember a darn thing about Laplace, is that something likely to be on a test? Okay. I can remember the first
I
one,
don't remember.
but the
No,
second
I'm
But
not
one,
gonna
this
give it
lab,
a
if you look at the homework,
there's lots of Laplace on it?
well, no, what it says is, so we gotta use the traditional method, the Laplace transform by hand, and then the left test by using MATLAB.
Son of a gun.
So we do have to go through this so we
Well,
understand it.
because you have the model, right? The only thing that changes is the equation.
We hope.
Okay.
So, in the Laplace, Laplace by definition is given by, if you have a function y of t, right? Then the Laplace of y of t is going to be equal to capital Y of s, right? This is the notation that's used in every textbook. The Laplace, you take the function and you make it big. For example, if it's f of t, the Laplace will be capital of S. If it's g of t, the Laplace will be g of s, right?
Where
And
S
so
is,
forth.
where S is position?
Yes.
Okay.
Now, this is y, what did you say, what s?
Is position
No.
or displacement?
S, no, it's not displacement, it's a complex variable.
Okay.
Right. So, but how is it defined? It is defined as simply the integral between 0 over infinity of y of t exponential minus st dt. Because you are integrating with respect to the variable t, only s remains in there, okay? Now this Laplace is used a lot in controls, okay? So when you go to the next class with Dr. Mead, you will see,
Laplace of the yin yang.
you know, an input,
Laplastered.
an output, so f of s, and input of s, output of s, the gain, we call this the gain, which is the output divided by the input and all that kind of good stuff. I don't know to how much detail he goes into,
Hopefully not.
but that's really what it is. Now, the property of Laplace, the property of Laplace is that there is the Laplace of the first derivative and then there is the Laplace of the second derivative. And you go like, why the heck are you giving this? Because, remember, our goal is to always solve this, right? This involves the second derivative, this involves the first derivative. So the idea, when you solve this, is you take the Laplace of the left-hand side has to equal to the Laplace on the right-hand side. Now, the benefit that you get when you do this is that the ordinary differential equation becomes an algebraic equation, right? And people like to work with algebra rather than differential stuff, okay? So the Laplace of the first derivative is simply sy of s minus y0, and the Laplace of the second derivative, so Laplace of y prime is equal to s y of s minus y of 0, and the Laplace of y prime prime is s squared y of s minus s of y0 minus y prime of 0.
Is there a table of Laplace transforms? in
Oh,
our book?
yes, they are everywhere. In my days, that's where you used to use, you know, just Laplace tables, you know. You get the function of time, you get the Laplace function, and the idea is, sometimes you have the Laplace here, you can get the time function, so you dance back and forth between the two, okay? And that's why the MATLAB is great. MATLAB, if you have a function of f of t, you just say Laplace of f of t. It gives you the function as a function of s, as you will see in a moment. It's quick.
What is that last one, minus y prime of 0?
Minus y0 minus y prime of 0, yes.
It's in the sheet.
Yeah,
in the
it's
sheet.
right.
It's in the sheet, it's all,
Yeah,
it's
look
all
down
there,
there.
you know? I don't even know I'm writing this, I shouldn't be writing this. Let's look at that in another example, okay? Imagine you have y prime prime, y
Because
prime
you do two
prime,
things at once or something.
minus 10 y prime plus 9y equals to 5t. Okay, let's pretend you have that.
That's in there too.
And with those two initial conditions, and you're asked to solve what is the function of y of t that satisfies the differential equation. Okay? Now, but you're told to do it using the Laplace. What's the first step? You take the Laplace of both sides of the equation, right? So you take the Laplace of, you know what, maybe I should bring this on the screen. It's probably easier to follow than to,
Easier on you.
I mean, instead of writing a lot on the board.
It's not in the
Trying
laptop.
to do big sense.
It's not downloading it. You have to use the lap, right? The laptop.
Yeah.
And then you use the lap machine. It's not in here that you can download, yeah?
I don't think so.
Okay.
I mean, we can type in.
Nothing is gonna.
Oh, that, yeah, we have it in the lap.
Yeah, I mean, because it gives us an example, so we can follow the example
In the MATLAB.
in MATLAB.
But you see this last, left.
Yeah.
You say last
Right, I
place.
guess that, but then how do I know how to do
Last place.
so?
It's Laptop.
This.
French.
Oh.
Just in the box.
How do I write?
Oh, this is on the table, that's when you have to go to the table.
Yeah, but where's the table?
Well, they have them in map, for example.
They have them everywhere. You can-
Yeah,
you
but
can-
not in our vibration book, right?
He may have something maybe in the back.
I have- I have to look at it yet.
Y double prime.
Okay, I'm right here.
Tell me.
Is that?
Yeah.
Yep, we
Yeah,
got
it's
it.
up, it's up.
We got it.
Okay.
So this is the one, so we're defining the Laplace as y of s is equal to the integral of y of t minus st. Laplace transform of the first derivative, Laplace transform of the second derivative. Both of those involve the initial conditions, by the way. Now, solving the differential equation by hand using Laplace transform. So this is the suggested differential equation.
Right there, he says.
And how are you gonna do it? Well, you take the Laplace of the left-hand side. Now, the Laplace of the left-hand side is L of y prime prime minus, so you're just adding L, right?
This
You know?
one.
Okay.
And 5, I think the right-hand side is what? Is equal to
5t.
5t.
it's
So
five
5L of t, okay? Now, using the appropriate formula from the table of Laplace transforms, now L of y prime prime using the second derivative is S2 y of s minus S of y0 minus y prime 0 minus 10 Laplace of the first derivative has two terms plus 9 L of y is simply y of s. And the Laplace of t, by the way, is 1 of S2. Okay?
Is
That
what?
means it's 1 over
Over
S
Oh, 1 over
squared.
One over S
Yeah.
squared.
1 over S squared, you know?
Yeah.
So this become, so all those key functions have been tabulated, right? And you go online anywhere, you can find what those things are. But you see how this equation here becomes this equation? You see? After incorporating the last, what do we have? We have S2 minus 10S plus 9 y of s plus s minus 12 is equal to this. Then you go like, okay, it's not taking me anywhere, right? Because remember what the goal is. The goal is to find y of t. Y of t,
Where's Y
okay?
S?
Now, from here, we can find what y of s is, right? And let me tell you what the idea is, because if you have a function y of t, if you apply the Laplace transform to it, what do you get? You get y of s. That's when you go from left to right. Now theoretically, if you have the Laplace, you should be also able to get L, y of t,
Y of t.
by
Just do it
going
backwards.
and getting the inverse Laplace. That's the cool thing about this method, right? Now, it's very easy. It's very easy to, well, yeah, that's true. It's very easy to get y of s from here, right? From this equation. And there are rules when you do the transformations, because when you have big stuff like this, you need to make this function as something over s squared plus something over s minus 9 plus something over s minus 1, etc. You know, you can divide it into different parts. It says here, we are seeking a function y of t that satisfies this the differential equation. At this point, we find the Laplace transform of y of t, okay? In order to find the solution, all we have to do is to take the inverse Laplace transform, okay? But before we do the inverse Laplace transform of this MATLAB can handle on its own, right? But I remember those days where they made us actually expand those, doing partial fraction expansion.
Oh, man.
Oh my God, it takes a long time to do that.
Right.
But, you know, by doing so, before doing that, let's notice that in the present form, we'll have to do partial fractions first, twice. However, if we combine the two terms, boom, boom, boom. The idea is this, is to take this y of s and saying that you take everything that is in the denominator. It's going to be something over s squared, and then another with s. If we had s cubed here, it would be a over s plus b over s squared plus c over s cubed, right? And then anything that is in the denominator will have something. And the idea here is to evaluate what these constants are, okay? What is a, what is b, what is c, what is d, okay? That means you have to expand this, make sure it is in the same form of this, right? And then you equate equal terms. When you equate equal terms, as you can see here, no, but this is truly how it is done. This is truly
Just
how
I
it's
simple.
done.
believe you, but
I'll
are
just
you
skip
serious
this.
about wanting us to use
Why
the
do you need to
traditional
skip this
Laplace
part?
by hand?
Was that?
Are you serious about part 2 of this, doing it by hand, all those partial fractions?
Well, you know.
Yes.
Give it a try. It's-
That's a yes.
Just give it an honest try if you can. But you get the constants. Once you get the constant, then it's an easy walk back to find the inverse transform. You get 50 over 81, 9 over 5t. This is just from tables, because the inverse transform of 1 of s, you know what that is. It's just 1. This one, the inverse transform of 1 over s squared is just t, right? That's why you have 5/9 of t. The inverse transform of 1 over s minus 9 is exponential 9t. And then s minus 1 is exponential of t. Then you have your
Where is
function.
that listed?
Now, some of you may go like, oh, man, that's,
Yeah, that's
but
me.
it's a complicated one nonetheless, right? Now, MATLAB, see how easy it is, MATLAB?
Sure, if you know what to type. And
How
you
many
know your
lines?
Oh, man.
How many lines in
That
MATLAB?
didn't
You're
work.
just defining f of s. You don't have to do the partial fraction expansion. Well, actually you do,
Yeah,
right?
you do. And
Because
not only that, you gotta type
What,
it
what in
right.
MATLAB, what I entered is this function right here. 50 over 81 s plus 5/9 s squared. F of s, and then I just, the little f is simply I Laplace. That means inverse Laplace of f, which gives you immediately, it spits out the function. Right there, which is exactly what we have here. Okay?
Looks like it's an easy one, see, easy plot.
And then easy plot of f, you know, just to kind of plot how that function looks like, and then that function will look like this. If you were to plot it as a function of time.
I know how to plot it.
Looks like these are-
Now, let's look at Laplace transform, but not by hand this time, you know, just using that. To compute the Laplace transform in MATLAB, we make a call to Laplace of f of t, okay? So this is done using symbolic computations. So for example, it gives you some very simple examples here. Symbolic s and t. So if it's 5, that means 5t to the power of 0. You say Laplace of f, what does it give you? Answer 5 over s. It gives you, it's symbolic form, that's the cool thing about it. For example, if you say Laplace of t to the power of 7, I mean, you're not gonna integrate e to the power of 7 or t to the power of 7 times e to the power of minus st.
Yeah,
You would have to
the same thing.
You would have to
I'm
do
getting the same thing.
integration by part about 6 times before you get an answer, right? But MATLAB does it in what? In no time. It gives you 5040 over S8. Okay? So Laplace of t to the power of 5, the answer immediately 120 over s to the power of 6. So this is the part that I wanted you to kind of sit there, and with MATLAB on, it's not like a very big script or something like that. You just kind of
Just
do
do
it.
this part and copy it?
Well,
Flat? Yeah.
you just go through it. Anything that is written like in here in blue or in the thing, as a practice stuff, right?
Okay.
And then I gave you different functions there, Laplace of e to minus pt, et cetera, et cetera, et cetera. And then, so here, in this part, in the first part, is when you're given the function of time and you're trying to find the Laplace, right? And the second part is when you are given the function of s and you're trying to find the function of t. That means this way you're going Laplace, the other way you have to do the inverse Laplace, okay? So the inverse Laplace of 1 over s cubed gives you the function of time. So you see how you dance around between the two, s, t towards s, or s versus t, right?
$30, but.
I Laplace of s over s squared over 4 is cosine 2t, right? If you are given f of s given in this form, right, then you just write it as f of s equals 5 minus 3s divided by 2 plus 5s. So, and then you say I Laplace of f will immediately give you the function of time. Okay, so that's really what that lab, even though I don't see that any of you have gone through that, practice those commands, but you're expected to do so.
Yeah, I'm about to
And-
try, but I.
Right now.
And just to make sure that it is done, that's why I had this to do by hand. Using, well, the assignment is that using MATLAB practice the commands shown in the body of the lab.
Right.
Okay, so it's, the commands are there as you follow, you know, you're gonna go through those. And then the differential equation here that I put in, I want you to use the traditional method. So what is the characteristic equation here, for example, going to be?
R squared
Plus
plus
R minus 2
minus 2.
equal to 0,
to 0, right.
okay? And,
I'm not too worried about 1 and 3, I'm worried about 2.
you know, one thing I need to take out from here, because do you know how to use to solve non-homogeneous equations?
Hell no.
Okay. So let's put this equal to
Not
0
just no.
then, right? Because it becomes, that's when we get to chapter 3. Non-homogeneous equations is another important thing, because the solution to the non-homogeneous equation will contain what? It's the sum of two solutions. It's the homogeneous solution plus the particular solution. Does that ring the bell a little bit maybe?
It was 25 years
Oh
ago.
my God. Oh, it's gonna be interesting. Oh.
I don't like hearing that.
Why you stand?
Particular solutions are very important because that's what happens when you do damped vibrations and. Oh.
So you're saying I should drop this and take it?
No.
Not
You know,
liking
I
that,
was
Rob.
just, you know, this class is what it is. I mean, it's not,
I
you
know.
cannot you cannot make it look easier. And you cannot, you know, you cannot dumb it down, if you will.
No, and
It is what
so
it
I
is,
know there's
you
some,
know.
there's a point to doing the transforms by hand, but I'm not gonna try to do them here.
Right, so let's,
Yeah.
let's do this, solve the
Do it.
equation, here put x equal to 0 instead of that 5t.
Thank you.
Because it's gonna, at least it's homogeneous, it's pretty straightforward, the two initial conditions are given, right? So do it using the traditional method, using Laplace transform by hand, if you can, you know, try at least to kind of,
Try to,
Give it a
I'm
little-
trying to get it set up.
because the steps are in the previous one, so at least you can, you know, fiddle around with it. And then you should get the same answer, by the way.
Yeah,
Whether
I know.
you use method 1 or method 2, and then using Laplace transforms and using MATLAB. In
I'm
other
just gonna
words.
try to follow your example here in the book in MATLAB real quick, so I know
And then the last question is pretty straightforward, takes 2 lines. Find the plot of function that corresponds to the transfer function. So you really just enter this function f of s, and then do easy plot of t. MATLAB.